In any case, the first thing, which I may have to remind people, Tuesday, I'm going to give you Monday off. You can have Monday as a holiday, but then Tuesday is actually Monday at MIT. We do this once every spring term. The people who schedule things want to have the right number of Mondays, Monday, Wednesday, Friday classes, and the right number of Tuesday, Thursdays. And the way they do this in the spring, they always have to turn a Tuesday into a Monday. So next week, I'll be lecturing Monday or Tuesday and Wednesday, which will both be in this room at 9 o'clock. Okay, so if you go to 26100 at 11 o'clock, have fun. And you can watch the video later. And actually, you're getting the videos up within a day or two now, right?
They should be going up pretty quickly.
Yeah.
Every couple of days.
Yeah, we had some problems earlier this week, but I think it's all resolved. So they should be going up fairly quickly. Anyway, so Monday, or Tuesday and Wednesday, I will be lecturing in here at 9 o'clock. Simone will be doing both Thursday and Friday of next week. Okay, as far as that goes. So we've taken care of that. We talked about the Blackhawk washer yesterday, or 2 days ago, and so I actually brought a couple of my little pieces left over from 15 years ago. This is actually the washer, and 15 years ago it cost $350. This one's painted gray. Actually, that means it's a Seahawk. This one's green. This would be an Army part. This one's steel. This one's aluminum. Don't ask me why. It's actually a very clever design. Instead of in order to keep it tight, there's a different number of holes in this than there are in here, and so no matter how you turn it, within about 2 or 3 degrees, you always get one hole to line up, and so they put a screw in there to keep the thing from loosening. They don't use lock wire or anything, friction or anything. They actually have a positive thing. Because if you lose your tail rotor, you just spin to the ground, which is exactly what happened. But the reason they lost their tail rotor is this washer in the incident one developed a stress corrosion crack. I don't know if it developed it there, but we actually took this one, which had never been used. The reason there's a saw cut there, we measured there's some flats here that keep this thing from rotating. And we measured the distance very precisely, within a fraction of a thousandth of an inch. And then we made the saw cut and we measured the distance. And depending on whether it shrinks or opens, you can calculate from it's basically just a simple circular beam, and you can calculate how much stress it took to open it or close it. We found 8 KSI, we measured 8 KSI residual stresses in this part, and it turns out with the type of heat treatment for the alloy it's made out of, 5 KSI would cause stress corrosion cracking. And the solution was to go to an overaged T73 heat treatment, which has a stress corrosion cracking minimum of 25 KSI. So they had been making it out of something that was only good for 5 KSI stress corrosion cracking resistance. They later switched to 25 KSI material, which is just a heat treatment change. It's not a compositional change. And then they, the residual stresses were 8 KSI, so everything fit together in terms of explaining it. So that's just filling in on that. Now, a question, I kind of said, oh gee, I wish I had brought Backoffen with me, but fortunately they didn't erase my wonderful drawing over here. We were talking about necking and void formation in tensile test, and that's what, these are graphs out of Backoffen. So you're doing a simple uniaxial tensile pull, and here's the fractured specimen. Here's necking. If you actually look at, in this case, a piece of copper, you actually find in the neck, if you cross-section and do metallography, you actually find a bunch of voids that are forming in the neck. Okay? The neck goes into a state of triaxial stress. Okay, we'll talk about stress states later, but it's basically it goes into a hydrostatic tension, if you will, and that's what's helping the voids open up. The whole thing's being pulled in all 3 directions. If you look at a higher magnification, you actually see these elongated voids, and you actually can see some copper oxide particles. These little black spots are inclusions, copper oxide inclusions, and in the holes, they're actually acting to nucleate something. This is all, oh, it's 906. This can be official now. This is, I think, out of Hosford's. This may be in your book. Hosford has some pictures, and you actually can see the fracture in the neck, what we call ductile dimple rupture. This is a cross section, and you can kind of see the cross section of the dimples and how the voids are forming, pulling apart. Classically, people will say, well, this is looking down on the fracture in the scanning electron microscope, and you see the ductile dimple. It's like taffy pull at 1000x, okay? 3000x, okay, sorry. Actually, it's even bigger than that on the screen. But anyway, inside many of these, you'll see the oxide inclusions that are nucleating each dimple, okay? So that's classic ductile rupture. I've now preempted Dr. Belmar on ductile fracture. Anyway, so these things do sort of fit together. Backoff and I has this drawing. If I had something with no inclusions and it was just a nice, very clean material, and I pulled on it, it might neck down like this. I get tremendous elongation. If I had something that was, and you do this is just a thought experiment, that the inclusions basically break this thing up into a bunch of fibers, if you will, okay, smaller tensile specimens. And when they neck down, it's like necking down a bunch of fibers, and now the total elongation with inclusions is a lot less than the elongation if the material was very, very pure. And in fact, that's true. We know that's true. Back in the 60s and 70s, we spent billions of dollars coming up with vacuum arc remelting and all these fancy things to get rid of inclusions in metals because they are crack starters. In fact, all the crankshafts and all the piston engines and aircrafts have to be triple vacuum arc remelted now, because vacuum arc remelting essentially burns away the inclusions that formed from the regular steel making process. So they make the steel, cast it into an ingot, and then they take this great big ingot and they arc it into another mold. So you got a round ingot that you cast, it's got full of dirt and inclusions, and then you basically arc it into a copper mold, and you withdraw the mold, and you just remelt it, but it's in a vacuum. So now in the heat of those little pieces, little spatter of metal going across there, they're being melted in a vacuum now, and it sucks out the oxygen and the nitrogen, and you end up with a very clean steel. They will triple vacuum arc remelt aircraft landing gear, crankshafts, the shafts for turbine engines. I mean, this is all, you know, they're using steel for these things, and they're triple vacuum arc remelting them to get rid of the inclusions once, twice, and 3 times. And you're actually getting things that are so clean that you look at them at 500x and you have a hard time finding an inclusion in the microscope at 500x. And there's standards for all these inclusion counts and things like that. So then someone brought up, one of you brought up, or asked me something about, and I said, yeah, we call it orange peel. Here's a picture of orange peel. I think this comes out of Hosford's book too, probably chapter 16. This is, I don't know what it is. It looks like it might have been a gas tank, the bottom of a gas tank or something in the automotive industry, but it's a drawing from a stamping from sheet metal, and the surface looks like an orange, right? I told you it did, right? There it is. It looks like an orange. It's caused by large grain size. Those little pebbly surface, each one of those is actually about the size of the grain size in the material. If you want to avoid this type of imperfection, I'm not going to call it a defect because it really doesn't weaken the material, but it does. If you wanted a nice fender on a car, it wouldn't be very good. Okay, the paint wouldn't cover it up. So it's not generally desirable. You have to control the grain size, and we'll talk about that at a later time. The other thing I wanted to do is, I could tell on Monday, going back several days, when I was talking about redundant deformation and how, I guess I can find it, but anyway, how you look at the deformation zone geometry, and if you're at a delta of 1 and it's just sheet rolling or something like that, everything is kind of straight line deformation that had kind of X's in there. But if you get to a delta 4 or 10, the slip lines all have this curvature to them. And I tried to say when the slip lines are straight, you have uniform deformation, it's homogeneous deformation. When they start to curve at higher delta, you have non-uniform deformation, you get inhomogeneous straining, it's redundant deformation, and the redundant deformation comes from the fact that you actually have to bend it one way and then bend it another way and then bend it another way. And I kind of said that, and some of the eyes were glazing over at that point. So here's my example. 2 decks of cards held together with rubber bands. If I deform it, I shear. Remember, the plastic deformation only occurs in shear. Hydrostatic compression or hydrostatic or tension has no effect on deforming the metal. It might allow it to go out to a higher elongation, but it doesn't cause the shape change. The shape change is due to shear, so if I do a shear on this, there's something at a delta is equal to 1 type of shear. A delta is equal to 5, you basically shear it that way, you shear it back the other way, and then you shear it that way to get the same shape change as delta is equal to 1. You did 3 times the work to get to the same thermodynamic state. Okay? Remember, in thermodynamics, the end states are state properties, and they tell you the energy or the shape of the material in this case, but they don't tell you the path. And the path, it's not, the work is not a path independent property. It's work is not conserved, and the work, the shear work, to go this way, back that way, and then this way again, I get 1 shape change for 3, but I pay the price 3 times in terms of energy, right? That's redundant deformation. That redundant deformation leads to inhomogeneous flow, okay? And that, a lot of that inhomogeneous flow comes from friction, okay? So this is out of Backofen, and this basically shows you delta dependence of inhomogeneity factor for copper strip with different types of lubrication. So here's delta, and this is basically copper strip where, you know, you've got something delta is equal to 1 is the height and the width of the deformation zone are equal, right? Here you're really in a rolling situation. Over here you're starting to get to something a little more towards drawing or extrusion. In any case, you can change the diangle of the draw, right? Anyway, unlubricated, the inhomogeneity factor as you get to higher and higher delta increases. And we saw that in that little handout that I just gave you, just passed out, when we went through and we saw the different delta operations. The inhomogeneity factor increases when you have less diangle, okay? And then if you got paraffin, oil, or soap, and remember soap are the stearates, and later we'll talk about why stearates are such good lubricants, okay? We also can talk about why if you live in an area with hard water and you take a shower, you still feel soapy even though you've rinsed off. Does anybody know about that? Anybody live in an area of hard water like San Antonio? You lived where?
Ridgewood, New Jersey.
Oh, okay. If you have a lot of calcium in your water, that's what's called hard water. In fact, the amount of calcium in the water is called the hardness, okay? And there's soft water, like New England has nice soft water. Take a shower in New England, rinse off, you feel nice and you don't feel slimy and soapy. But in San Antonio or certain parts of New Jersey, they probably are using groundwater, not rainwater, but they're probably using well water in that part of New Jersey. Okay? Duh. How did I know that? Because it gets saturated with limestone and it gets a lot of calcium, and what happens is the soap is a calcium stearate. And if your water is already saturated with calcium, you can't dissolve off the soap. A monolayer of soap molecules, of stearate molecules, stays on your skin. And you can rinse till the cows come home, and you're still going to feel slimy when you get out of that shower, right? I mean, I travel around the country and go to a hotel, take my shower, and I can tell you what the hardness is of the water. Not exactly, but I can tell you whether it's hard or soft water. San Antonio has hard water, but I know that for other reasons. Okay, any questions? So now we want to talk about sort of forging type of deformations. This is almost a delta 1, not exactly 1, but close to 1. Not everybody uses delta, okay? Back often liked to use it, and his students, Hosford and some others, like to use it. But you go back before the 1960s, and most people don't talk about delta operations in terms of deformation. In any case, this is showing two different friction levels and metal flow. You start with something that looks like this. You reduce it 8%, 22%, 33%, 44%, and 60%. And you can see the inhomogeneous deformation, okay? The rectangle turns into, the squares in this rectangle turn into, in the center, maybe there's still squares, but out the edges, they got funny shapes. And as you go further and further, you get worse and worse in terms of the uniformity of your deformation. This type of shape change, this would be a frictionless type of deformation, but you typically have something that causes this barrel shape. See intermediate in here? You can see why I call it a barrel shape. If you want to see the barrel shape in the real world, you can go to, this is Japan Steel Works doing upset forging of some big heavy something or other. If I can get it on here. Well, let me see. Let me try to do it. Yeah. I was looking for this book yesterday and couldn't find it. Anyway, it's because I had it on my cart. Couldn't find it on my shelf. Anyway, so here's upset forging of a big hot piece of steel, and you can see it starting to barrel. Okay. Things get pretty big. This is a 600-ton forging. Okay. The largest forgings we do, or the largest pieces of steels we do, are about 750 tons. So they don't get much bigger than this. Anybody have an idea why it looks kind of whitish right underneath the clamp? Because we broke off the oxide. In order to heat this all the way through, you had to leave it in the furnace for a week. And you're leaving it in a furnace, it's just an air furnace at about 2200 degrees Fahrenheit, and the iron oxidizes in the furnace. And the oxide's about an inch or two thick, okay, after a week at 2200 degrees Fahrenheit. And now you grab it with these big tweezers. They're big tweezers to pick up a 600-ton piece. And the oxide breaks off. The oxide has a different emissivity. I mean, it's not important, but when you actually forge this, you will have this slag, this hot slag of oxide. It'll all break off. And I remember the first time when I worked for Bethlehem Steel, during the summer, they had a little program to introduce all the 500 new engineers that year to steel making. And in the morning, we would listen to vice presidents give talks. This lasted for a week, and that tells you how many vice presidents they had at this company, that you could spend 5 mornings listening to the vice presidents. And they weren't long talks. I mean, these guys had a half an hour each. And then in the afternoon, we actually go down to the Bethlehem plant. And I remember going to the forging plant, and had great big forging presses like that. And this was 1975. Summer of 1975, and they had a big forging hammer slamming down on these things, and when the great big crane moved the steel back and they were done, two bare-shirted steel workers went out there with their shovels, scooping up all the slag, the oxide that had come off the forging. I mean, it was only about 6 inches deep there on the forging bed. You had to scoop it off, because if you brought another one in, all you do is forge all that stuff into the surface of the next one you're going to do. So it was all done manually with these guys, and it was amazing to me. I sat there kind of bug-eyed. They had a dumpster that they had brought up, and one guy would scoop. He'd go down to scoop, and the other guy, and then he would come up and throw it over his shoulder into the dumpster, all this hot slag at about 1000 degrees Fahrenheit, okay? And the other guy would go down, and they were like pistons going back and forth. And I said to the guy, I said, what if one of them got out of sync and threw hot slag in the other guy's face? And the guy says, well, they've been doing it for 30 years. And the guys who do throw it in the other guy's face, they probably don't work there anymore because they may be dead. Okay, but
How does that die?
the die starts out cold, and by the time you end up forging, the anvil, which may only be 4 feet thick, okay, and the hammer above, which may be another 2 or 3 feet thick, you don't want to touch it. It's probably pretty warm. It might get up to 1,000 degrees. You're forging something at 2,200, and you're hammering it. I mean, go watch the blacksmith here in the basement, okay? You know, he starts out with a cold hammer, and he hits something hard, and when he's done, that hammer gets warm, but it only gets to about half the temperature of the thing you're forging. Now, if you keep on hitting with that same hammer and don't let it cool off, then you're going to have a problem because it heats up, and now you're hitting. What you're doing is you're taking one material that's softened by heat and another material that's strong by low temperature, and you're using the hard material, the cold material, to form the hot material. And that's actually something I was going to talk about next week. There's 3 ways we can form things. We either start with something that's really, really hard and form something really, really soft. And remember those little machine screw things? That's cold heading. That's all at room temperature. No temperature effect to give me a strength difference. What do I do there? I heat treat the steel to 200 KSI strength, and the workpiece is going to be 30 KSI, annealed steel, soft, as soft as I can get the steel. But as I'm working it, it gets up, and that final part is probably 100 KSI, but the tool is still 200 KSI. Okay? I got to have some good lubrication. So that's a case of same temperature, but I'm using big strength differences to give me my advantage. Then I can use temperature as the advantage, but now I have this process that's not isothermal. I have to have a cold tool in a hot workpiece. And now I have to have a little time in between my working for the tool to cool off, right? And that's kind of your question. Yeah, it gets hot, okay? And the third one, which we'll talk about, is called isothermal forging. And it was developed because of Al Backoffen and superplasticity in 1965 when he rediscovered it from Germany. That's Tuesday's lecture. Okay, I don't think we'll get to that today. Isothermal forging is how we make a lot of the turbine disc for airplanes, jet engines and stuff. But it basically is, I mean, that sample should be in the Smithsonian. I recovered it from the graduate student's desk. They were using it as an ashtray. Okay.
And will they just let the forming tool anneal, or will they try to touch it?
No, actually, in superplastic forming, you get material that instead of taking a 30% stretch, will take a 400% stretch. So you come in with, you can use graphite dyes, okay, which are not particularly strong, but you get the material up to where it's like clay, okay. You take the superalloy, the nickel-based superalloy, up to 2,200 degrees Fahrenheit, and it will deform like clay. But you have to have something that's a little stronger, but it can be something that's relatively weak, like graphite dyes. You can use molybdenum dyes, you can use other superalloys that have a little bit more temperature, okay? The dye materials are, you're limited in your dye materials, but everything is hot. It's isothermal. The dyes are just as hot as the workpiece. And you're using something that's a little bit stronger, but you're using a material that's super plastic, okay, in isothermal forging. We'll talk about it next time. I have to explain how you get superplasticity first. Okay, but we could not build the jet engines that you fly on. When you fly on, you know, United or Delta or American or whatever, you're flying in a whole different technology than in 1960 when I flew up here to come to school as a freshman. Okay, it might have been jet engines, but boy, they're a lot different. Okay. Okay, now I did want to show you one other thing in here. I actually had a lot of things that I could show you in here. But the one I really want to show you is This one, okay? This is James Naismith's painting of his patented steam hammer, forging the propeller shafts. This is a 30-inch diameter shaft for some Middle Eastern kingdoms, Brunel's, okay? Is Brunel in the middle? I think it was Middle East. Anyway, they were building a ship called the SS Great Britain. It was going to be one of the largest ships. These were the largest wrought-down forgings of their day. It was just a steam hammer, big steam cylinder up here, just a hammer, and they're going to take some ingot of wrought iron. This isn't even steel technology. This is wrought iron technology. Look at the manipulator they have back here. Count them, okay? There's actually men moving this thing. You got an anvil right here. Notice the shape of that anvil. It's V-shaped. Remember I showed you the picture of how you don't want to do deformation at delta is equal to 5 of just two platens coming together, because you'll crack the inside. It goes into tension. But if you do it from 3 sides, use a V-shaped anvil, you will actually get compression in the center. You can drive the center into compression and not cause splits in the center. 1839, they had studied back off it. They knew all about delta, and that's why they were using their V-shaped anvils, right? Just want you to know. It all, someday I ought to tell you some stories on Al Backoff. He was an interesting guy. Actually, I'll tell you one of them right now. I'll tell you a couple of them right now. So when I came back, when I was a sophomore, I had worked 2 40-hour-a-week jobs that summer between freshman and sophomore year. Well, I'll tell you even more. It was during the Vietnam War, and I was lucky enough, took a test to get a summer job. I grew up in Virginia Beach, Virginia, to get a summer job, and I scored high enough on the test. This was not the hardest test in the world. It's a civil service test, and you had to be able to add 2 and 3, rather than just 2 and 2. I mean, really hard questions. And I got above a 95. I may have gotten a 98 or a 99, but that was high enough that I got hired as a postman. And the job I had the summer before, I got paid $1 an hour as a clerk down at the beach in Virginia Beach, clerk in a drugstore. Well, the post office paid me $3.05 an hour. Okay, that was the standard rate. And I was basically replacing postmen who were going on vacation for 2 weeks during the summer. They hired a bunch of subs, and I did all kinds of jobs. My favorite part of it, into the summer, they had me delivering special delivery letters, which is like express mail today. This was before FedEx, and for 35 cents you could pay to get the letter delivered, special delivery. And so typically I would show up at 9 o'clock in the morning. They would give me 10 or 12 special delivery letters that had to be delivered immediately in Virginia Beach. So I'd get in the station wagon and I would drive for the next 8 hours, because Virginia Beach at the time was the 5th largest city in the United States by area. Okay, we don't have to get into the reason for that. Chesapeake, Virginia was the 3rd largest, okay, by area. They had incorporated whole counties under Virginia law into cities so that Norfolk and Portsmouth wouldn't annex them. But anyway, I just did tell you the story. Anyway, so they're paying me a little over 24 bucks to deliver $3 worth of mail, right? And we wonder why the post office is going broke, okay? They've had this model of service with a smile and at 1/10 the cost for years, okay? It goes back a ways, so anyway, so the next summer I needed to make my $3 an hour to pay my MIT tuition and all this other stuff. So I worked, I did the civil service thing, and they hired me at the Naval Air Rework Facility where they rebuilt jet engines. And we got all these crashes coming back from Vietnam, and we'd have to rebuild the engines. And I was just an engineering trainee and stuff. But then that was only $2 an hour. I needed to make that extra $1 an hour, so I took my old clerk job back at $1 an hour. And I worked 80 hours a week at 2 jobs 30 miles apart, and it was not a great summer, okay? So I came back here and I decided I would work in the lab. And I'd taken my mechanics of materials class, my first materials course other than 3091. Al Backoff is the professor, and I went up to him at the end of the class. I said, Professor, would you have any jobs in your lab that I could do? And he says, well, come back to me next week and I'll let you know. Well, he came to me at the next class. He says, I found a job for you. Go see Tony Thompson. And so I started working for Backhoffen. And he was a very kind man, as long as you weren't his doctoral student. If you're a bachelor student or master student, he was just a gracious gentleman. White hair, always wore a bow tie. Okay, looked like an academic, the kind of bow tie academic with his tweed sport coat and stuff. And anyway, so when I started, they put me in that little short door, 8137. That was my office. It was Backhoffen's graduate students. Backhoffen was leaving the week that I came. He had retired in his mid-50s. He couldn't get along with anybody. He decided to heck with it. And he was leaving MIT, and I was starting. But he always had kind of had a, he had liked me. I'd been one of his undergraduates, and he came to me, knew I was starting, and he gave me a piece of advice. And the piece of advice is, the only way to keep your sanity around here is with a pocket full of Valium. Okay? I've always remembered that. And he went off. He had a home up in Marblehead. Now you got to remember, this is 1976. And he and his wife decided they would put it on the market for an outrageous price, $90,000. And if anyone offered it to them, they would just move to New Hampshire, to their farm in New Hampshire. Well, the first person who came by offered him $90,000. He obviously didn't have a clue what this place was worth, and he sold it, moved to New Hampshire, and about twice a year he would come back when I was an assistant professor, and he'd always stop by to see me, okay, and ask me how I was doing, okay? And I would ask him how he was doing. Well, in his later years, he only passed away about 2 years ago in his 80s, he had started a tree farm, a Christmas tree farm in New Hampshire. This was before you could buy nice pruned Christmas trees. And he would go out there in the spring, and he would spend his time out there pruning the trees, and he would sell those trees for $3 a foot. So if you want to buy a 7-foot tree, it's like $21. Well, in 1970, I mean, this is ordinarily you'd be paying $3 for a Christmas tree and be all scrawny. He was leading the market. Nowadays, you get all these pruned trees. Everybody prunes trees, but he was one of the first ones. He was selling 10,000 trees a year and making about $50,000 or $60,000. My salary was $15,000 as an assistant professor. Okay. The other thing he would do up in New Hampshire and Vermont and Maine is he would go out and he would go to the yard sales and buy the junk, and then he would take it to New York City and would sell it as antiques. So what's one man's junk is another man's treasure, okay? And he told me he was making more money than he had ever made as a consultant or as a professor, okay? So Al Backhoffen was a character, okay? Anyway, maybe someone will tell a story about me being a character someday. Anyway, so I want to start showing you some of the types of flow you get from inhomogeneous deformation. Here's a forging. Hot upsetting of steel with sticking friction. Well, sticking friction means the stuff around the tool doesn't move at all. The material is stuck to the workpiece. And all you have to do is not put the glass lubricant. Typical lubricant for hot forging, well, in the steel forging, like I showed you, you don't use any lubricant. You just let the slag fall off, okay, the oxide scale fall off. But if you're doing a nickel-based superalloy or something, you actually encase the whole thing in a glass frit. And when you get it up hot, you now have this syrupy layer of glass because the glass melts and gets thick. And if you pick the right glass that's at the right forging temperature, it'll be a good lubricant. Anyway, so this is one they did without any lubricant. And you can see the material flow lines initially. This material right underneath the tool didn't deform at all. This material might as well have been a part of the tool. That stuff, the flow lines, it was like, you can think of it as grains of wood in the original billet of steel, and it just shrunk around like here, bowed out. But notice how it's now curling around, and you're going to form a defect if you kept this thing going. You're going to get a little lap, okay? So that's the effect of friction, and you can see the inhomogeneous deformation. This material didn't get worked at all. This material got, this direction, that direction, a number of times, okay? So that's where inhomogeneous deformation comes from. Let me give you another example. This probably comes out of metal forming by Alton, but this is a titanium blank, which is actually an alpha and beta microstructure initially, and it's been squeezed down, and the microstructure afterwards from the etching, you can see it looks like it's fairly uniform. A little barreling at the ends, but I mean, it flowed fairly uniformly. This is an all beta microstructure. Titanium comes in alpha form and beta form. Alpha is hexagonal close packed, beta is body centered cubic. If you try to forge something in the alpha beta range, good deal, okay, nice uniform product. You try to form it in the all beta, look what happens. You get shear bands, localized shearing. And all this other material, you got the big coarse microstructure, and then you got these bands here in between. See, you see the X from the delta is equal 1 type of deformation? Basically, the stuff's tried to shear on these simple little X planes. The X kind of got distorted, but see the X? Okay? Those are the shear bands. Now, let's look. This comes out of, well, this might come out of Hosford. So, one of the things people do, they actually take modeling clay. I'm not kidding. They take modeling clay. Now they do it. They do a finite element analysis in the computer. But in the old days, they would take modeling clay. They would put two pieces together with nice flat surfaces. They'd scribe grids on them, and then they would extrude the two pieces through the same die, then pull it apart, and you could see the flow lines from these things they started with. And here we have different die angles, okay? 40, 45, 60, little thing, another thing with a different angle. And this is actually Don Blickweed again, my old boss when he was vice president of Bethlehem Steel. Okay, those actually may be steel billets rather than clay, but anyway, cold extruded billets. Okay, but if you start looking at, this is someone else's data, but if you look at the hardness number, so they're now looking at hardness and different amounts of deformation, the distance from the center. So you're looking at hardness across something like one of these billets. And with zero deformation, of course, it's uniform. Everything's nice little squares. And of course, with zero deformation, your low hardness number, if it's steel, let's say that's a Rockwell B50 something, very annealed steel. And as you go up in deformation from 4 to 6 to 13 to 26, you'll see that initially you get very inhomogeneous deformation across there based on the hardness numbers. You get a lot of deformation and everything becomes homogeneous again because it's all fully kneaded, okay? You've really beaten down that pizza dough. So if you're going to make a pizza that's going to have a uniform crust, this is the practical things in this course, you've got to knead it a reasonable amount. You don't do something in between, okay? If you do nothing, you don't have much. The first stuff introduces a lot of homogeneity, and you really got to get to 40% deformation. I mean, that's 40% stretch is a fair amount of stretch before things start to get homogeneous again. Okay? So I used to think when I was a bachelor student here, and I was doing wire drawing for my thesis to make superconducting wires, that I would do better if I would do, I had a great big set of wire dies, okay? You could buy diamond dies for 20 bucks a piece back then, so I had a government research contract. I went out and bought $1,000 worth of dies, and I had them in 5% increments, okay? Well, that was the wrong way to go. You really should be doing 30 or 40 or 50% draws and not 5 or 10% draws. Because with 5 or 10% draws, you get lousy deltas, okay? You get a high delta operation and you're liable to crack the center, okay? And you also are going to get very inhomogeneous deformation when you do high delta. This is the highest delta operation among these four, okay? But in any case, so that's one thing to remember that if you're gonna work it, you got to work it a lot. And I guess I do have another story on that. So I still got time. You know, I never know what story I'm going to tell. It's just a question of what. I mean, I think about it ahead of time, believe it or not. So here's the trolley wire again. Okay, so this is trolley wire. This trolley wire has got a equivalent delta of about 30. Okay, super fine grain. It actually is starting to get to the region, I believe, of super plastic, made by Phelps Dodge. But the company that originally had bid on this, this was for the Northeast extension of Amtrak, the Excella line from New Haven to Boston. There's a $330 million federal contract to build this line, and that was the product they wanted to do. They had to purchase somewhere between $4 million and $7 million worth of copper to mount it. And I get a call about, I think like December 21st, saying, Tom, can you go to Rome, New York? There's a little company that's making our trolley wire. This is from Amtrak, the Amtrak engineer. Can you go to Rome, New York? So we drive out there on the 22nd, and they say, oh, by the way, we need an answer before Christmas. That's not very far away from December 22nd. But what they had is this company had been making the largest wire. They had been making copper wire for years, but the largest diameter they had ever made was 5/16 of an inch. That's over half an inch equivalent, okay? They had never made anything much above a quarter of an inch in diameter. And the largest mold they had a continuous caster. This was the size of the largest mold. It's like 1 3/8 inches or something. And you can see the grains, okay? There's a longitudinal cut and another cut. Huge grains. Remember I showed you earlier, I showed you the orange peel and stuff? If you have large grains and you deform something. And the Amtrak's question was, are we going to have problems with this large grain size? Because the company said, well, we're meeting your spec except we don't have small grains. Is that okay? Okay, that was the question. And so I'm supposed to give the answer before Christmas, okay, by going out there and looking at this. Well, it turns out I told them on the 23rd to reject the product. $4.5 million worth of product. Okay. Well, turns out it was a fixed fee price contract with the U.S. government, and the company had certified to the U.S. government that this company in Rome, New York, that had never made wire bigger than 5/16 of an inch, was the only company in the entire world that could make this trolley wire. Okay? Because the Amtrak had some very tight specs. This is a copper silver alloy. It had to have a certain amount of elongation, you know, when it's, anyway. So mechanical properties. And so I didn't realize all this stuff, but I had rejected it. I told the Amtrak to reject it, so they sent a letter saying, we reject it, you can't put this up, you have to go find other material. But they had already certified there was no one in the world that could make it to the Amtrak specs. Well, it so happens that Phelps Dodge, the second largest copper company in the world, had been begging this company for 2 years to make a bid on this. And the problem was their alloy was so good and had all this redundant deformation and superfine grain size that it had, Amtrak for some reason had a spec of between 8 and 14% elongation, and this stuff had 18% elongation. It had too much elongation. It was too ductile. It was too good. It was outside. Why someone said the elongation should be between 8 gave an upper limit. Ordinarily the elongation, there's just, you have to meet a minimum, right? And this company had not allowed Phelps Dodge to make a bid because they exceeded the maximum when there should have been no maximum, okay? But that's how they had written the spec. And so technically, they wouldn't let them bid, even though it was going to be a much better product, okay? And actually you can see, I mean, I got some, you've seen the tensile bars, I sent them around. They neck down, you know, big, you know, stretch, right? What it really meant, it turns out Phelps Dodge price was going to be $6.5 million or $7 million, and this other company in Rome was going to be $4.5 million. And so the money in the pocket of this British company was going to be an extra $2.5 million of profit if they could convince the government to buy this junk, okay, their junk, okay? But I had rejected it. So it goes to a 1 week long arbitration down in December at a ocean resort in Old Saybrook, Connecticut. Anyway, there's a lot, this thing goes on forever, but The bottom line was when they gave the arbiters the briefings, the attorneys gave the briefings, the British company was arguing how Tom Eager was just absolutely insane and incompetent metallurgist to have rejected this material. He had no basis to do it, and it cost us $2.5 million, and the government owes us $2.5 million extra because they forced us to go out and buy the Phelps Dodge material. Well, okay, the briefing from the government was, you committed fraud on the federal government. You told us there was no one else willing to bid on this in the entire world, and we found out that Phelps Dodge has been trying to bid on this. And so the bug-eyed attorneys from the British company realized, ooh, we could be sued criminally. And in fact, that's exactly what happened. A week after the arbitration, the FBI raided the offices of the British company, took the passports of the senior managers, took their computers, and at that point I was out of it because, okay. But I mean, don't defraud the federal government. That's one of the claims. I mean, Amtrak has the legal authority to put you in jail if you tell them a lie, okay? Now, other companies, they tell lies to each other all the time, but it's not good to do it to the federal government. They can do things. The other part of that story was the way we actually won with the arbitration. There really was nothing in the literature that said you couldn't do this, okay, that the grain size should be a big problem up there. But it turned out it was essentially an orange peel effect, a large grain size effect. Even though Amtrak had told this company, don't you dare install any of that wire, they took about a 10-mile stretch down here in Providence and they installed the stuff from Rome, New York. And they ran the train along that 10 miles and they videotaped it. And the pantograph, which is the carbon brushes that are running along there, it turns out there was a rough surface on that wire. And as the thing's going along at 60 miles an hour, it looked like the 4th of July. This thing was sparking all over everywhere. If they had put that up for a couple hundred miles, they would have had to take it down 2 weeks later because it would have just eaten itself to pieces from all the electric sparks. And the idiots were smart enough to videotape it for us. So, well, you know, but you never said that at the time. The fact is, I didn't know that was the reason to reject it. I did actually look at some data, and this guy Tony Thompson that I first worked with Backhoffen, he had done his doctoral thesis on grain size effects of fatigue in copper. And I went back to some of Tony's papers and stuff. Okay, but anyway, so there's another little story of how I got myself in trouble. Okay, sometimes you just have to make a decision, you know. And sometimes you're going to end up, I wasn't sued directly, but Amtrak was sued for $2.5 million because of my decision. But we ended up proving ourselves right because they provided the evidence for us, idiots. And then the bottom line was I don't know what happened to their criminal proceedings. Anyway, this is extrusion. And if you go with just straight edged extrusion dies, you can have different types of things going on, but in fact, you end up with dead zones, and I'm going to show you some of those dead zones in a little bit. This is what they call backward extrusion. You actually push a tube tool down into the billet, and up the center of the tube comes your extrusion. So it's a question of what's moving. Is your press stationary or is your press moving? But you end up getting dead zones, and I want to show you some of those defects. Well, here's one of the sets of defects, or inhomogeneous deformation. This is copper. This is a copper casting, and you can see the grain structure from the original casting, and they extruded it part way, and pure copper over here. This is 70-30 brass, done the same thing. Look at the dead zones. Copper has a little dead zone. You can see the grain refinement. Now this is a reduction ratio, if this is axisymmetric, which it probably is. It says a billet, so it probably is. This is a reduction ratio of about 85% on both of these. Well, not both of these, but anyway. But look at the shear bands in the brass, okay? So the different work hardening between copper and brass gives you a very different pattern and gives you these dead zones. And you know, that type of pure shear, it not only does it raise the forces necessary to do the extrusion, but it also ends up giving you lousy surface finish coming out of that die. Okay, because you're rubbing metal against metal. It's galling wear, if you will. It gives you a lousy surface finish. Now, so the last thing we'll do is we'll talk about Stamixco, which we were talking about with some people a little bit before. So this is if you're doing polymer extrusion, so you got an injection molding press. So it's like a great big toothpaste tube. Now it might be 30 feet long and stuff, and made out of steel that's 3 inches thick, but it's just a toothpaste tube. And you're going to squirt polymer out of this and extrude it into something. Well, part of the problem is, a lot of times, it's like, as you said earlier, it's like a two-part epoxy. You want to mix two polymers together, and if they're very thick, it's hard to get them mixed well, okay? So this is what they call a static mixer. That's where the name Stamixco comes from. And pretty simple tool, but there's some technology goes into the design, believe it or not. And you basically have this type of thing that goes into your extruder barrels, or goes in line. You've got your pressure ram, and then you got your dies and everything up here. But the polymer melts or polymer materials in a partially molten state are going to be brought in here, and you put it through all this, and you get it to mix. And so here they've taken kind of a blue plastic and a white plastic, and they're being brought in. You got blue down the center and white on the outside, and you go through these things. There's the three-dimensional model, and in just a few lengths you've got light blue. It's mixed. If you tried to do that without something to create the turbulence in there, it would take you a half a mile, okay, with things of this viscosity. So this is extrusion of viscous polymers, and it's got all kinds of, there's the kind of starting material, a blue core, outside tube. And so turns out this guy, who's an MIT chemical engineer, he's got a PhD, he's a nice guy, very nice guy. He came to me once, we'd done some work on something else, and he came to me, he'd gotten together with these guys, and he actually had run this as a test for students at some polymer extrusion conference, and said, here's an extrusion we did with the blue resin in the center, and we start the extrusion, and when we're all done, the blue resin is on the outside. It's not on the inside. How did the blue resin get to the outside? And he had a $500 contest for the students. He wanted me to run a contest at MIT, see if the MIT students could do it. Because out of like 50 students at this conference, only one young woman figured it out. So he was just so proud of his thing. Anyway, so does anybody have an idea how the blue resin got to the outside? Yeah. Nope, not diffusion. What have we been talking about? Inhomogeneous flow, right? Basically, if you had looked at this thing at some step in between, you would have found that you had the white sticking by friction along the boundary on the wall of the mold, and the blue bulging in front. Right, so here's blue, here's white, and here's blue. Now keep doing that for a while. And the nose goes up further and further until finally the nose folds over on itself and turns 180 degrees. So now look at the top here. See the noses? See how it folded over up there? If you had seen it at an intermediate stage, you would have seen essentially this stuff bulging in homogeneous flow. So he was very disappointed to find that I could solve the problem in 5 minutes. Now, I didn't give you 5 minutes to solve it because we didn't have 5 minutes. But anyway, and we were talking earlier that it's partly because I think in terms of deforming metals and things. Here's a polymer problem. He was a chemical engineer. In his mind, and actually if you read some of the stuff, he explains this in terms of a boundary layer. That's because a chemical engineer or a mechanical engineer understands boundary layers, and they think of the world in terms of boundary layers. And I mentioned, what's your name?
Mark.
Mark. I mentioned to Mark before most of you came to class, I had a problem once, which was a problem in current flow through copper and steel when we were doing welding, and the steel would go from being ferromagnetic past the Curie temperature and stuff and become non-ferromagnetic, and so this is going to really affect the way the current flows through this thing. And so I went to see Jim Melcher, who was one of the great scientists at MIT. He passed away about 15 years ago, and we started talking diffusion. And to me, diffusion is you have a vacancy and you have one atom move into the vacancy and it changes places. Jim Melcher started talking diffusion, and he drew me an infinite series of parallel resistors. He thought of everything as an electric circuit. I thought of diffusion in terms of atomistics. Mike Mousakis thinks in terms of the flow in Stamixo as a boundary layer problem. I think of it as inhomogeneous deformation. Okay? So even though we're all engineers, we speak different languages. That's one of the lessons for today. Okay, I'll see you on Tuesday.